Today I want to talk about atoms. Atoms. We talked about the rotational spectrum very quickly, and then we talked a little about the vibration of molecules. But the molecules are made out of atoms, and these atoms can also be excited, and they can absorb light and so on. Now, I will just want to get you talking. I've talked too much, and I don't want to talk so much, so I want you talking. So we start with what is an atom, and we take the simplest atom, hydrogen atom. And so the idea which is in our head, it must be like a planet going around the sun. So there's a heavy nucleus and an electron going around it, and so we have this motion. And we've done that, classical mechanics. We've done it for the satellite, or for the planets. So what's wrong with this? Why can't this be an atom? Why is this not a good, or is it a good picture for an atom? It's not. Why not? Yes, it's the smallest part of a molecule. So there's another atom here, and they together make the make the molecule. And my picture is, it's just a proton there, an electron going around. So what's wrong? Paper? What's the dimension? Well, this is it's half an Angstrom. So it's 0.5 times 10 to the power minus 10 meters. So it's very small. So is this your picture of an atom? Paper? It's a sphere. It's round, okay? So mine is not round. Mine is what? Yeah, it's flat. Huh? It's like a pancake, and I want a little ball, and I have a pancake. Huh? I don't want pancakes, so there's something wrong. Oh, well, that's one thing that's wrong. What else is wrong?
I think there isn't electron orbits.
There isn't any?
There isn't electron orbits, but the probability distribution for the electron, not the orbits.
Not the orbits.
Yeah, but the probability distribution. So the probability to Heisenberg principle.
Okay. It's right what he says, but let's go a little slower. We don't jump there immediately. Here's the electron. Goes around here. Okay, like a.
How can you determine the distance between the nucleus and the shell?
And the atom.
Force of attraction?
The force, yeah. The force is the same as the force between the sun and a planet. The potential goes like 1 over r, and the force like 1 over r squared. And this is E squared. So it's like the Speak up, please.
Uncertainty principle.
Uncertainty principle. Okay. Yeah. So this guy's right. So he says this. I can't say it's there. It's somewhere there, but not there. Huh? Okay. But other things that are wrong.
I think so. It should be an
Well, maybe. But it doesn't change it to. It could be elliptical, but it could be spherical too. Classically, yeah. No, yeah, classically. It could be. So what else is wrong?
Classically, electron must be fall down into the proton.
Fall into the proton. Why?
Because law of Maxwell laws, when electron change terms, you must give some photons and lost some energy.
So what Andre says is this picture isn't stable. What he says is this thing will actually move like this, and eventually it'll land in the middle there. And the reason being, I have a charge which changes it changes its position, and that is like a dipole. It gives radiation, and when it gets radiation, there's less energy, and so the thing has to. So the first thing is it can't. There must be something that keeps it there. If that's just my picture, it's wrong. No? That's a good point. And there's another point which I think one needs to make. It's connected to your point, and that is atoms have a specific size. So when they lose energy, the size becomes smaller. But we don't get small hydrogen atoms and medium hydrogen atoms and large hydrogen atoms. We just get hydrogen atoms. They are of a very specific size. So they can't be on any orbit. And so this was a problem at the beginning of the previous century, and it was sort of solved by Niels Bohr. And most of you must have heard about the Bohr atom, the model of the Bohr atom. So what is it? What did Bohr say? Yeah. So what he says, there are specific orbits which are stable, and in those orbits which are stable, it does not radiate. This is the first statement. So there are stable orbits, and he had a formula for them. He said that the orbits are m times v times r must be equal to nh bar. So this is what he said, whereby n can be 1, 2, 3, and so on. And so by just claiming this, he got rid of the problem which you had. He just said there are orbits where it doesn't happen, okay? Where it doesn't radiate. And then he made another important statement. Does anybody know what Bohr's other important statement was? This is the stability. So this would also say why all the atoms, all the hydrogens which are in their ground state are of the same size, because there is such an orbit and they're all of the same size. So we got rid of that problem that we have small ones, medium ones, and large ones. So they're all of the same size. Now, what was the other thing Bohr said? Well, he said this radiation, it's about radiation.
When the atom absorbs some radiation,
Yes?
they return chance to the...
Yeah. So he says when, say, we have an electron here, and it wants to go there, it just jumps there. Huh? So it doesn't go around and send, it just jumps. So electrons jump, and then he had a formula where the final energy minus the initial energy is equal to? Yeah, well, they say, h nu, and this can be n times h nu, depending on how many it jumps. But assume it jumps just one at a time. So what did he solve with that statement? Why did he make that statement?
An electron cannot just stay in the middle or between two energy levels. It has to be n and this one at the bottom of this one, but not in between.
Yes, okay. So that's what he said. It can't be, it must jump. It can't just be in between and so on. But why did he want to say that?
Jumping of electron is related to the emission of the discrete quantity. When an electron is jumped from one shell to the other shell,
Yes.
it releases the discrete form of energy.
And then?
And then goes to the lowest energy level.
Yes, but why did you want the discrete energy levels? Anybody? Why did you want discrete energy levels? Discrete values of this frequency? Because they were seeing them all over. They were seeing straight lines in the spectra of light spectra. You weren't seeing a broad spectrum like in the black body radiation. You were seeing in various metals and so on, you would see a very specific, say a yellow light and a very sharp light. And they could do that spectroscopy, and there were these different sequences which were already experimentally well known, the Lehman sequence and so on. There are different these sequences, and so there were these specific lines, and he got and through this he could find them. And with this little thing, this little model which he put forward, he could actually find that the frequencies of the lines for hydrogen. So he could find in hydrogen, you would have a line from there to there, and these states were given, and you'd have another one like this, and these were these different orbits, for which he has a formula, and he could calculate how long these, what the frequencies would be, and it fitted. And so he had a fit to a lot of experimental data. Okay, so this is basically Bohr's model. So isn't that wonderful? No? So what's wrong with it? You already said to some extent, but let's just recap. So we have a big success. We have atoms which have a fixed size. All our atoms are equally large, which we need to do all sorts of things in solid state and so on. We can't say, well, this solid state is built up of small atoms and this one of bigger atoms and so on. They're all the same. And that's an important thing. And so he got that right, and he got the stability right, because he just said they can't give off light if they are in these stable orbits, and he's got the spectrum right. So that's a lot. So what's wrong with Bohr's model, or is it nothing? Yeah.
It was valid only for the object atom and in a plane dimensional plane.
Yeah. So the first point is very important. When they tried to expand this model to other atoms, to try to understand the forms of the different atoms, how many electrons they have, and things like that. He couldn't do that. And you say to the plane, yeah, we discussed it already. Atoms are round and they're not pancakes like planets move in a plane. And so if you move in a plane, then your atoms would not be round. And there was one other problem which came up somewhat later, and that is he assumed that this state, the lowest state, had angular momentum of h bar, 1 times h bar. And if that would be true, then you would have had a magnetic moment. If you have an electron moving around this, it's like a current moving in a circle, and so that produces a magnetic moment. And the electrons didn't. That was not in agreement with the experiments. And so Bohr's model was close, but was wrong. But it helped a lot. And even today, people will say, well, this is from the lowest Bohr orbit or the higher Bohr orbit or something like that. So they will still talk about the orbits, but nobody works with Bohr's model. And so we need something else. Now, so what we need to do is calculate the hydrogen atom, or for that matter, any atom, in quantum mechanics. Now, someone had mentioned also these things locate an electron at a point which is not good, because we know we can't have the momentum and the position at a specific point. But that came later, this idea. Bohr couldn't have known that. So I want to discuss the hydrogen atom, but it's very, very technical. There are lots of formulas. I have a lovely little book, this one. It's called Understanding More Quantum Physics. And it has a most beautiful summary of all these things. And if somebody wants to have a look at the book and maybe copy a few pages, you're welcome to do so. And this is basically the book in which atoms are described in the most concise way I've seen. So obviously we can't do this today. We can't do all of this. So I can just give you certain ideas of how it follows, and you can then, if you want to, those who want to, can study some of these things in detail by themselves. I'll just try to specify what are the main ideas without going through all the mathematics of all these ideas. So the main idea, of course, is that we start with the equation. And for V, we write minus, and in general, we can write Z, which is the charge of the nucleus, over R, and this is very often written in this way in books in atomic physics. That is written as the potential, but that is not in SI units. So if you want to write it in SI units, you actually have to put in here 4 pi epsilon 0, and this thing has a specific value, and then the whole thing is in SI units, and then you can calculate energies in what? In joules. Then they come out in joules. The way these things are normally formulated is that we do not put this in, and the energies eventually come out in electron volts. So let's not worry about that. If we want to work in joules, that's what we have to do, and you have to add it into the formulas every time you see such a formula in a typical book like this. A book of quantum mechanics normally does not work in SI units. This is another strange thing in physics. When you talk to cosmologists, they don't work in meters for good reasons. They work in parsecs or something like that. They have different units, which you can convert to meters if you want to. So let me stick to the typical literature there and take that out. And now we are not in SI units. And if you want to go into SI units, we'll have to put that back. Now, how do we write this now as a Schrödinger equation? We want to do this in quantum mechanics. Okay, so this is the equation we have to solve. And so without knowing any physics, we can write this thing delta squared. And the mathematical expression is, if we do it in Cartesian coordinates, it's the second derivative with respect to x, and with respect to y, and with z. And if you do it in polar coordinates, that thing becomes 1 over, I think it's 1 over r squared. Yeah. Times r squared and then let me write this down just that I don't make mistakes. Okay, and then of course we have this times psi is equal to r plus v times psi is equal to e times psi. Now this quantity is found in books which have nothing to do with physics. It's just the question, if you want to formulate a del squared operator in spherical coordinates, this is what you write, and you have to solve that problem. It is typically also done in electromagnetism, and it certainly has nothing to do with quantum physics. But in quantum physics, we get to know a lot of this thing, and we have a specific procedure to work with it. And that is, we call this thing here, we call L squared times going on to psi, or L squared we can write as h bar squared minus h bar squared, and then all these things behind it. Exactly this. And so so what you have to do is you have to find the eigenvalues of this operator here for various eigenfunctions. And these eigenfunctions are called, who knows what they're called? Avipa? They're called spherical harmonics. So what I can say now is that this operator, if I add this h bar to it, is equal to an operator. And if I apply that on the so-called spherical harmonics, then I get L times L plus 1 Y Lm. And there's a H bar here because I put it there. But the H bar is just because I put it there. But this is a function of two angles, theta and phi, and it's called a spherical harmonic function. And it is the function with which you use to expand the angular part of a quantity. And they are listed, and you can find them. I can show you some of the spherical harmonics. For instance, we do that here. Y00 is just this. So it's normalized in such a way if I integrate over all the angles, of both angles, I get 1, the square of this. And then Y1 will give me 3 over 4 pi to the power half, and cosine theta, and so on. Cosine theta, and the next one, this is the Y10, and these values 0, 0 here are L and M. I just want to tell you, I'm telling you this because this is material which you can find in any textbook. You can find it in quantum mechanics textbooks and textbooks on solving three-dimensional problems in general. You will find these functions. They are called spherical harmonics, as I said. You have one. This value can be plus or minus 1 here, and that is I will try to quickly tell you how one could do it differently, but I think a lot of courses in quantum mechanics are devoted to doing this sort of work, finding the functions which, like the spherical harmonics, and these spherical harmonics, by the way, are built up from Legendre polynomials and so on. And so there's a whole mechanism of doing this. It's not particularly difficult, but it's a long slug. It goes on and on and on to do this. So I don't want to do that, but I just want to show you that this is the way this problem is analyzed step by step. But when you see what we've done now, we have taken, if I do this now, I take this operator and I replace it by its eigenvalues, which are L times L plus 1. This is a differential operator. It's not operator in the sense of quantum mechanics necessarily. It's just a differential operator. Finding the eigenvalue problem of that differential operator would give me H over 2m and then 1 over r squared ddr r squared ddr, and then I have plus v of r. V is just a function of r, not of the vector r. And then I have, I think it's minus. No, it's plus, I think. No, well, let me see. I want to, this operator works on the function ylm, and so it gives me L times L plus 1 h bar. No, the h bar is in front. H bar squared is in front, over L to the r over r squared down there, and then there's the potential, and this thing operating now on a function which is just a function of r and this y lm theta ylm theta phi is equal to E times. Okay, so this is the expression which we get, whereby I didn't do it for you. I just said this thing. There's a function defined called a spherical harmonic, which will give the eigenvalues of the L times L plus 1, and I will get I think I must be a little careful here. The h bar squared goes here and it goes here. From there. And there's a minus sign, and that makes that a plus sign. Okay? And so I have this equation now, and I want to the operator, this operator, the angular operator, I've already applied to that, and that gave me the eigenvalue here. By applying that operator onto there, I already have the eigenvalue. What I'm up to is to look at this quantity here, which is minus z e squared over r plus h bar squared over, well, this 2m should also go there from here, 2mr squared over 2mr squared and there's L times L plus 1. And so I again call this thing an effective potential, as we did in the classical case. So in other words, as in the classical case, we have taken out this quantity and put it towards the potential, and then we are left with a equation which just depends on R. It's this thing, just depends on R, and these things go away then. So this effective potential we can now draw. So it looks like this for L is equal to 0, and for L is equal to 1 it looks like this, and for L is equal to 2 it looks like this, and so on. That is the effective potential as I change the values of L. And L here can only have the values 0, 1, 2, and so on. And that comes from the differential operator, the eigenvalues of the differential operator, which I tried to discuss very briefly. And so we're looking now for the eigenvalues of this equation here. And so we will have one here for L is equal to 0. The energy of it will be like this. Here we are. This operator plus that is still giving the energy. This gives different forms of energy, and these different forms of energy we can identify by various quantum numbers. We know it will depend on L and M, and it could depend on another number which we call N. And so we're trying to, and so this will also depend on N and L, this quantity there. And so the next state could be there, this one, but there could be one here too. And the question is it below or higher or lower or the same? The differential equation which you solve is quite different for this state than it is for that state. Because here, that is the effective potential. It's a different differential equation. And then for this one, where the effective potential is this. So we have two different effective potentials, and we get solutions there. And then we have another one here, and there could be similar one here, which is in this thing, and there could be another one here. And so you get these different solutions, and they are given by the solution of this equation given by polynomials which are called the Laguerre polynomials. They are also well documented, and if you look them up in the book and so on, you can find them, and I can write down a few examples of the Laguerre polynomials, but let me just draw them. Let me just draw this one, the solution of this state. It looks like that. And the solution of this state, can somebody guess? What would that solution of that state be? it will have another node. It looks something like that. Because I'm looking at the solutions. I'm looking at the solutions of this potential, one-dimensional potential. And like any system, it will look like this, that the lowest case is just one bump. The next stage is one bump plus is this bump with going through 0 once. The next one will be like this. And so you can look at the Laguerre polynomials and you will find that they look like that. So that one here goes like e to the minus z r over a. And that one there goes like 2 minus z r over a0 e to the minus 2r over zr over 2a 0, and so on. And so you get the solutions of any of these will be like this, that they have the lowest solution is just a thing that goes like this, the next solution goes like that, and the next solution goes like this. And so this is a typical spectrum of a typical sequence of ways the solutions look. And these Laguerre polynomials, of course, do exactly the same. But what is interesting in this whole aspect is that the total energy is given. All these energies which you get here are given by some constants which turn out to be 13.6 electron volts divided by n squared, like in the Bohr model, exactly the same, where the value of n is equal to 1 plus nr, which is, this is nr, and this is 0, 1, 2, and so on, plus L. And so so here L is equal to 0. I put L is equal to 0. I take the lowest state, and so here I have n is equal to 1. And so that state is at minus 13.6, there's a minus sign here, minus 13.6 electron volts. And the next one is only, will be with n is equal to 2 here, so that's minus 13.6 divided by 4. And that can happen in two different ways. The one way is by going onto this guy, this solution, and taking the lowest value. But that solution has L is equal to 1 and NR is equal to 0. So L is equal to 1, NR is equal to 0. So this has an n is equal to 2, that state. And in the same way, that state here, which is on the, it has an L is equal to 0, and an n is equal to nr is equal to 1, and so it's also 2. So these two states both have n is equal to 2. And just in the same way, the next state will have an n is equal to 3 in different ways. And so let us just make a little table. And we say here, let's look at all the states which have L is equal to 0. There's a state there. Its value is nr is also 0. And then there's a state here where nr is 1. And then there's another state where nr is 2, and so on. And at the same value, we have a state with L is equal to 1, nr is 0, and this, and this. And then we have a state L is equal to 2, and it starts up here. And then this is the pattern which we get. And for those who know spectroscopy, what do I call this? What do I call this state? The ground state, yeah, but there's a specific notation for spectroscopic notation. We call these S states. All the states with L is equal to 1. If you look in a book, you will find this is a 1S state. And this is a that's 2S, 1P. So we have this notation S, P, D, and so on. So there's such a notation. So if you look at the book, what the different states are, they will be normally given by S, P, D, and so on. Okay, so now we have, just by talking without doing the mathematics, we have the spectrum of the hydrogen-like atom. So we have to do one more thing in the hydrogen atom. If we want to look now at other atoms, we want to look at helium. So the hydrogen atom, I want to look now at other atoms. The hydrogen atom has an electron here. Now I want to look at helium. Where's helium's electron? It was also here. So it's also sitting here. And why can it sit there? Yeah, so this is a very important new thing we haven't really covered. It is that electrons have spin. We've talked about photons having polarization, going around this way or going around this way. Or in another way, we could see if that is the direction of the proton, then they could go this way or that way. Yeah? So photons actually have spin 1, and it's a special case that there are only 2 directions. But a spin half particle, which is an electron, has 2 positions. So this state which we have found here can accommodate 2 electrons, and that will give us helium. And then if we go up here, we fill these states now. We put in more and more electrons. The whole thing, of course, we have to change Z, and the whole spectrums move and so on, but that doesn't matter. We just look at this pattern. We will be able to put 2 in here, and we will be able to put, does somebody know how many I can put in there, in the P? 6. Okay, so why are there 6? So it is because, does someone want to answer? Why are there 6? Yes. So we have to go back to this equation, and here we have the L values can be 0, 1, 2, 3, and so on. And so what the M values, minus L2, yeah. So this can be 1, and it can be 1, 0, minus 1. And this can be 2, 1, 0, minus 1, minus 2. And so they go up like this. So this is part of the property which you just get out when you do that, find the eigenvalues of that operator, that there are these values. And so we can put in 6 here. And so if we look at this, what is the total? 10. 10 up to here. Huh? So which atom has 10 electrons? Neon. What property does neon have? It's what? Inert. Yes. It doesn't have any free electrons. Huh? So it cannot interact easily. Huh? So that is a direct consequence of this scheme. And now we can go further. We can put in another 2 here. And now I want to put 2 in here. So I have 14 now. What is that? Silicon. And so that is the atomic structure of silicon. And silicon is the stuff with which we will make electricity from the sun. And it's this guy that has this structure. And you dope it, and the guys will explain to you what doping means, by having a atom, by replacing one of the or some of the silicons with what? Who are the dopers? What comes just before silicon? Phosphor. And just after silicon? Chlorine. So you can dope. So if you have silicon and you sometimes replace some of the atoms by phosphorus, you you have basically the same structure, but you're missing a couple of electrons. And if you put in chlorine, you basically again have the same structure, but you have some extra electrons in the solid material. I think we need to break, and I would just, I'm not sure whether we should break for the day. Maybe you should do that. Just break for the day, yeah? So then you can go. Just wait a bit. Just wait a bit. I will be staying over here tonight. And if I say you can break for the day, I mean you can go and work on your projects. That's what I mean by breaking for the day. Okay? And then I will be around this afternoon, and I will also be around this evening. So if people want to ask me something, I will be around. And also tomorrow morning. And tomorrow I will again give a shorter lecture, but I will try to explain to you. Actually, I wanted to show you something about angular momentum. Angular momentum has a very, very nice properties too in quantum mechanics, and maybe I'll do a little bit about that, and then I would just like to show you what all this, the effect of all this is on the bands in the materials. So how do you get, how do you make a silicon cell that produces electricity? What is it? I won't do the detail because we have a team of experts working on that, or developing experts. They are busy developing their expertise. But I will just give you, the rest of you, a sort of just a short idea of how these atoms sit in solids, and what the effect of that is on properties of solids. Okay. I'll do a little bit on angular momentum, just because this was quite messy. I didn't, but I think it's easier for you to go and read it up, and you can use my book if you want to, and it is available in many mathematics books, applied mathematics, I must say, and it's also available in all physics books on quantum mechanics. Will have something on the hydrogen atom. So it's what I tried to do is just to show you the steps, how this compares with the work which we have done already with the planets. We have done work with the planets. We have had diagrams of this kind, but they were meaning something quite different. Here they have a different meaning, but we still have the separation of the three-dimensional problem into a one-dimensional problem, and then solving a one-dimensional Schrödinger equation, and so on. And the solution of these things are not. I mean, if you can solve a differential equation, you can solve this differential equation. It's just another one. They are basically all very similar, and it's enough to just talk about what the structure of the solution is, and that's what I tried to do. Okay, so we'll see you later after 5 minutes or so up in the lab, and then I'll be around tonight as well. No? Okay. Huh?